Massaging your forearms is key to preventing carpal tunnel. Ladies and gentlemen, this is my favorite massage tool. With simply pulling the trigger, you can adjust the massage balls and you can massage your forearms with the desired pressure. It's really a beauty and I use it almost every day. In this video, we're going to study how this mechanism works.
This video belongs to a playlist called the Mental Mechanism Library, in which we're going to study products all around us, figure out how they work internally, and save their mechanisms in our Mental Mechanism Library. This is going to make you a better mechanical design engineer.
Before we dive into the CAD, let's appreciate and fully understand how the massage device works. By pulling the trigger, I'm going to pull it very slowly, and I want you to focus on this part right here, the sheet metal. The sheet metal part retreats, which allows you to remove the shaft that contains the two balls and slot them anywhere you want for the correct spacing. Also note that in the back, when you pull the trigger, there are more slots that allow you for more modularity, and they're all connected to the trigger when you pull. So the way it works is when you slot it where you want to, you heard that snap, which is caused by these snap clips, or rather called spring clips. Right there, there's one, there's another one, and that holds it in place. But what locks it in place, as you saw, is releasing the trigger. I want to study what's happening, and I want to teach you in this video internally that's causing this locking mechanism. I colored the components in the assembly so it's easier to follow along. First, let's give it a quick 360 so you can gain a perspective, big picture perspective as to what's going on. Now, we're going to do a cross section to understand what's going on in one of the arms so we can understand the mechanism. As the assembly loads, I want you to focus on this side where I'm hovering my mouse. In pink, we can see the sheet metal part that will be sliding along the x-axis from left to right in this direction. This is essentially called a spring return mechanism. So here we have the spring, and as you pull the trigger, so my fingers will be here, I will pull the trigger in that direction, and this will make the green part retreat and compress the spring, and as it retreats, the sheet metal part here in pink will also retreat in that direction, the direction where my mouse is going. And as it's retreating, we have these little fingers where I'm hovering my mouse. I call this the sheet metal fingers. And as they move to the right, they will leave the opening available for us to slot or insert the shaft, which I just clicked on here in blue. This shaft, you'll be able to slot it in once we move the fingers to the right. Now I want to focus on something called a spring clip. As we zoom in, this is what I call the spring clip. I'm going to hover my mouse. It's this U-shape injection molded part that's part of the housing, and it will act as the name implies, a spring clip, a spring made of an injection molded part. Just because we give something the name spring, it doesn't mean it has to look like a coil. So going back to the spring clip, imagine we retract the sheet metal part, so now there's an opening. We slot in the shaft, and as we're slotting it in, so this pink part is no longer present, as we're slotting it in, the shaft will come in contact with this face that I highlighted in blue, and it'll make the spring clip move to the right. It'll deflect it slightly, slight deflection, and then it'll pass through the little mountain here, and once it gets into the configuration that I'm showing you right now, the deflection, there'll be no more deflection, and the spring clip will come back to its original position like we see it right now in this screenshot, in this capture, this moment in time. And I think that's a pretty ingenious design. It reduces the amount of parts that are manufactured because the spring clip is incorporated into the housing of the device. So props to the designers for that. Lastly, I want to focus on this boss extrusion that sticks out to prevent the spring from sliding out. So let's focus on that geometry. I'm going to isolate the green part and the boss extrusion here. It's worth noting that the X design that you see here is because the part is injection molded. You can do more research on that if you wish, on injection molded parts. There are entire books on the subject of best practices for injection molding. But in summary, the boss extrusion, if it were a dome here without the X, it would create opportunities for cavities, which isn't good. Again, this is not a class on injection molding, but I wanted to bring awareness as to why some geometries look the way they do. Bringing awareness by itself is making you a better mechanical designer, and that's one of the goals of this video. Let's learn together. Why not replace the green boss extrusion with a press pin? So this extrusion right here, it could have been quite easy, I suppose, right? To install a press pin or some hardware that extrudes. It'll be cheaper in a sense. And the answer is because we want to decrease the bill of materials. We want to decrease assembly complexity and assembly time. All the things I just mentioned makes the product cheaper. And also note that most of the loads are perpendicular. There doesn't appear to be much of a shear force present. Therefore, the design that we're looking at now works. Keep in mind, there are always trade-offs when designing. And sometimes I wonder if there's an algorithm that one can follow, or if the only way is to just know this and be an experienced designer that takes all of this into account as he or she is designing on SOLIDWORKS. Tell me your thoughts. Have you ever wondered about that? Do we have to be walking encyclopedia when it comes to designing, manufacturing methods, and keeping all of this in mind as we're designing? Or is there maybe a sequence or an algorithm that we could follow that could facilitate that process for us, so we don't have to retain all that knowledge in our heads? Leave a comment below. I want to know your thoughts. As a bonus, I want to show you this locking mechanism. So we see the little lock and unlock with this switch. So what happens, I didn't show you this in the intro, so I'm going to verbally describe it to you. What happens is when you move the switch to the locked configuration, if you try to pull the trigger, if you try to move it in that direction, the trigger will be immobile. So that's what happens. And I wonder what is happening internally that's preventing us from moving the trigger once we slide the switch. It's actually very simple. Some of the simplest mechanisms are the most beautiful. As we look in the transparent, this is one of the reasons why I love using SOLIDWORKS to explain mechanisms. We can see through parts. It's very simple. The switch that I'm hovering over in the back that I was just showing you, the switch is connected with this fastener to this part here in orange that slides. So whenever you slide the switch, the orange part will slide. And right now it's in the locked configuration, which means that the bottom face that I'm hovering my mouse, the face right under here, is coming in contact with this top green surface, preventing us from moving the trigger in that direction, upwards. And once we slide this to the left, once we slide the orange part to the left by sliding the switch to the unlocked configuration, then those two faces that I just mentioned before, the one here and this face here, will no longer be coming in contact because this will be off to the left here. And that's how the locking mechanism works.